The year is 2050. The challenge: send a 35-person crew to Saturn's moon Titan. A group of young scientists have been commissioned to research and invent systems that will allow the entire crew to travel safely the 746 million miles to Titan, where important resources for sustaining human life have been discovered. I have been tasked with inventing a system that will shield the humans from dangerous solar radiation, protecting them on their journey from direct and diffuse solar radiation, including visible light, ultraviolet light, infrared light, X-rays, and gamma rays. We know that solar radiation is one of the main health hazards of space missions. The energy emitted from the sun is enough to change or break DNA molecules, especially when humans aren't being protected by the Earth's atmosphere. Currently, space agencies use layers of shielding around the ship and spacesuits to protect astronauts from solar radiation. However, this poses a problem: mass. They are limited by how much shielding they can add to spaceships while still enabling them to be light enough to lift off and exit Earth's atmosphere. My solution to this is microorganisms, specific bacteria that are resistant to radiation and can be propagated to form a shield that protects the astronauts. Only a thin, light layer in between the ship's interior and exterior walls would be needed. It would also have other benefits, such as research and waste removal. There is a species of bacteria called Deinococcus radiodurans that is resistant to freezing temperatures, dehydration, acid, and the vacuum of space. If there was a layer of this bacteria in the ship's walls, it could potentially block the sun's radiation. Deinococcus radiodurans can withstand up to 5,000 grays of ionizing radiation. It can also repair both single and double-stranded DNA that would be damaged by the radiation. Deinococcus radiodurans thrives in habitats that contain organic materials such as sewage, soil, meat, and feces. This means that the waste that the astronauts produce could be pumped into the compartment in the walls of the ship, which would provide nutrients for the bacteria to grow. This could be combined with Earth's soil to provide an ideal environment for the bacteria, which would also help to diffuse radiation, further shielding the crew. As the spacecraft travels farther from the sun, less bacteria would be needed for shielding, and so the crew could cultivate the byproduct of Deinococcus radiodurans, which is manganese, to repair tissues and produce important healing properties for the crew. Deinococcus radiodurans also converts solar energy to glucose, which humans need to survive. Byproducts of Deinococcus radiodurans could also be used to grow crops on the inside of the spaceship, because the soil and waste combinations are ideal for crops such as rice plants. The bacteria would cultivate the crops to grow on the ship while the crew tended to them, so they can produce oxygen and food. Further investigations are needed before this theory is to be feasible, including using mathematical formulas to extrapolate the amount of radiation humans would be exposed to the farther they get from the sun. We could test the limits of radiation exposure based on what we know, the impact of the longest amount of time a human has lived in space, and the amount of shielding that would be needed. Additionally, we would need to develop facilities that would allow us to test how the microorganisms respond as the spacecraft travels farther from the sun. On a personal note, my grandfather Raymond Smith was part of the team that invented the high-energy particle detector, which monitored radiation levels on the Gemini mission. The small device allowed NASA to collect data on how much radiation the astronauts would be exposed to. It was vital for the beginning of manned space missions. This is one of the reasons I've always had a passion for space exploration, and I can't wait to follow in his footsteps.